Hi, I've been asked to give a bit more detail about what I'm expecting in the lab, for Lab 9 and Lab 10, and I thought I'd do that now. So the idea is that we want to form a digital signal to drive a servo motor. And I had a bit of a chat about that during class, but I thought I'd reiterate it, right? And the idea is that let me try that again. The idea is that servo motors use a thing called pulse width modulation. Now, I hope you remember what happened in the lab when I showed you what the servo motor did. Servo motors are electric motors, but rather than just continually spinning at a given speed, or faster or slower, they position themselves and stop based on the input signal. And the input signal is a pulse width modulated signal. So what that means is, just say the servo motor can go between 0 degrees and say 359 degrees. Well, what happens is the control signal, each of these servo motors has 3 signals. It has a ground, it has usually a positive voltage, in our case it's going to be plus 5 volts, and it has a control signal. And that control signal is a pulse width modulated signal. What does that mean? Well, what it means is, at the low end, if you want the servo motor to point at 0 degrees, then it's not much of a pulse. It's at the low end of the duty cycle. Remember, the duty cycle for a square wave or a pulse, repetitive pulse, is the percentage of time that the voltage is at the high position. So let's just say for 0 degrees we might have a sequence of pulses like this. And now my drawing is pretty awful, but this distance here is supposed to be the same as this distance here. Let's call that T0. Okay? Then to get to 359 degrees, what happens is you make the pulses wider. The pulse this time is probably going to start at the same position, but now it's going to be much wider, and then it'll drop down again, and then again start at the same position, and then probably go off the end, right? So this distance here now, the width of the pulse, let's call it T359. Okay, and what I want you to do is to design a circuit that does that, based on switch inputs or based on some other input. And I think in the class the other day, I suggested a way to do it, which was to have a 4-bit counter. And you can look up 4-bit counters in the just on the web. Just Google 7-4 series 4-bit counter, and you'll find plenty of options. I think the one, I've forgotten which one I came up with. I think 74LS85, right? That's this guy. Actually, no, 74LS 74HC161 was the one I came up with. That's the other one is a comparator that I'll talk about shortly. Okay, so that's the counter, and all that counter's doing is it's outputting 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 0, 1, 2, 3. It's a 4-bit counter, so it counts up to 15. Once it gets to 15, it goes back to 0. Now, what we could do with that is we could say, okay, let's pick a number between 0 and 15. Let's say 8. And then we could say, well, if the number is less than 8, if the count of the output of the count of the counter is less than 8, then let's be high. And if it's greater than 8, let's be low. So what that'll do is that'll change the width. If we choose a different number here by selecting different switches, right? I've got 4-bit switches here, and at the moment they're all open. So this, I think I probably should do this the other way around. I probably should have pull down resistors and just connect straight to plus 5 volts here, but that's okay. What this is doing is you can then select the position of the servo motor, because changing the number here will change the width of the pulse. Now, how do you do that comparison? Well, there is a thing called a comparator. In fact, there's a thing called a 4-bit comparator, and that's available. And so by changing the number here, this is just going to be the number you set. It's a 4-bit number, and you're comparing it with the count on the 4-bit counter, you should be able to get a different width of pulse. Now I've just gone through in multisim, and I've made a circuit that does that. And if I run the circuit, right? So here's my the bottom trace here is my least significant bit. It's this one, X4. And the top one here is if A is less than B, right? And at the moment I have 2 switches closed and 2 open, and you can see the width there. If I close switch 2, right, I've changed the width of the pulse because my comparator is comparing it now to the number probably 7. So it's only going to be high, or sorry, this is less than this. It's only going to be high when the number is less than 7. And then I can close all of them, and now I should get, or maybe I'm getting all high, because maybe I can never get less than, maybe my number 15 can never be less than the count, which only goes up to 15. Right, I'm using the A is less than B output on the device, on the 74LS85. And if I maybe change the least significant bit, you'll see that we get a very wide pulse for the duration. Okay, and then I can swap those over, and that should give me a slightly wider pulse because I've gone from 1 to 2. And if then I go to 3, let's just wait for it to wrap and get a couple of those on there. And then if I change it to 3, I get a slightly wider pulse again. And then if I change it to 4, oops, that was 5, let's go back to 4. Right, it gets a little bit wider again. And then if I go to 5, it's going to be back to that wider one. And then if I go to 6, it's going to be a little bit wider again. And then to 7, it's wider still. Right, and I'm going to have to go to 8. And yeah, I didn't I didn't quite change the settings in time. But you can see what's happening, right? And I think that's about all I wanted to say. There are other ways to do what I've asked you to do. I know one group has taken a completely different approach. I'm okay with the approach they've taken, but I would like to see somebody do it this way and see how it works. Okay, that's it. I'm going to drop another couple of other people's YouTube videos that'll into the playlist for this course. Have a look at those too. They just explain a little bit more in detail about